You have permission now.
Got it. Okay, so recording is happening.
So you want to talk about the FL stuff, second level stuff? Do you want to like Jason like organize what is it the question? So to make sure that the things that you were thinking about are answered, or do you want me to like go a big overview of what is the stuff
So
there?
I think the specific questions I have are, well, there are some general questions, but that would basically be going over some of the new things that you have in the second level results GUI. I think they're general, but then in particular now the surface-based version of it, where you have options that are similar to what you had before. I had questions about what the most appropriate correction was. So there's now a mass base versus a size base. So we talked about that, but you also added the ability to change what the reference atlas is. So, which is, I think is really handy. So now previously when you would run you load some result, you do the correction, you'd see the clusters that were there, you could click through the clusters, you'd see all the stats table was there, and then underneath it would be a list of all the ROIs that were included in that cluster, or that cluster covered, and some like percentage of vertices or something like that. There was a default atlas that was based on. Now you can change that to the speech lab parcellation, so you can get like a list of the ROIs, which is very handy. And there were I think there were some things that I wasn't aware of that were there, that were probably there already, where you can right click and export these. But so I thought maybe Alfonso, if you want to just step through what those options are.
Sure.
And I had some other questions that were specific to just SEQ PDS. It's probably not going to be of much interest to anybody else.
Okay, let me see if I can share my window first. Can you see my window, guys?
Real quick, I'm probably going to head out, but quit the meeting.
Sure, no problem. And this will be safe, so if you want to see it later, that's no problem at all.
Okay, awesome. Have a good one, guys.
See you tomorrow, Ricky.
So can you see my window here?
Yep.
Okay, excellent. So yeah, this is kind of like the display for the second level results explorer window, which, well, before it wasn't. Before it was there was a different display function actually that was used when you were using surface-based versus volume-based analysis, and now I got rid of finally, because that was a pain to maintain, basically because it was very similar to the function for surface-based analysis was very similar in the GUI, at least in all functionality to the volume-based analysis, except minor difference, but they were two different functions, and it was a pain to support both of them. So I basically got rid of that, and now both of those surface and volume-based analysis are treated through this function and through this same GUI. So there are going to be some glitches, I'm sure, for a few days or weeks until we get it all sorted out, but it's for the better. At least for me, it's for the better. Anyway, so this is the function that looks at second-level results, either volume-based or surface-based analysis. And there are a few things, as Jason mentioned, that are kind of like new. The first thing that is new is that this is organized. Remember, typically you used to see something like this when you launch that window, and now the first thing that you see is none of those options, and you have instead a few kind of like default settings. And the general idea behind this is that there is some movement in the field as to trying to not encourage too much people fiddling too much with the threshold values and p-hacking, kind of like until they find something significant, by playing with all of the potential options in the GUIs until they find something significant, and then they report that they found that, and they don't say what is the procedure that we used to until they found the result. So to try to. So it's a little bit of a balance act, because you want to give users options so that they can use whatever method they prefer, but you want to like encourage not too much p-hacking. And that is why this change was made, basically to have a few kind of like default options that contain kind of like the recommended settings for every scenario. So I have like 3 recommended settings that all have like all of the details have been tuned for some like optimality criteria. And I think that they work best, basically, and those are kind of like default recommended settings. And then if you want to actually go ahead and play with those parameters, because in your study there are some good reasons to do that, then go ahead and do that, and that will be kind of like the 4th option in here, where you go ahead and play with the actual details of the thresholds, different thresholds that you want to use. So the organization change is basically that, it's trying to like organize people into using some like default a priori choices instead of having to everybody choose their own by playing with it until they find something significant. Okay, and now the three, and well, another change is that the three methods that are shown by default in here, the third one wasn't available before. So before you could do like parametric statistics that are this is basically how you determine that a cluster is significant. We talked about this before, but you have this Worsley like a tall random field theory approach that tells you that if you have like a field of Gaussian numbers that is relatively smooth, what is the likelihood of finding a cluster that is this large? And there are some formulas to tell you that tells you the probability of finding a cluster just by chance of this particular size. So all of those formulas can be used to determine significance at the cluster level, and this is the first approach, the random field theory parametric statistics. The nice thing about that is that it's parametric analysis, so they are like, they don't need to run any randomization studies. It's just a formula, so they are very fast to compute, and they are also very sensitive because they make all of these assumptions about your data. And the downside is kind of like the same thing. It's because they make all of these assumptions about your data. If your data doesn't follow those assumptions, then they might not be all that great. So that's the random field theory approach that gives you like statistics for each cluster based on this Gaussian random field theory. Then you have the second approach, which was also available before, is the permutation randomization analysis. Instead of trusting like random field theory to tell you how significant a cluster is, you can actually randomize the data and just run a bunch of simulations and do through this kind of permutation randomization approach and actually see under the null hypothesis what is the distribution of cluster size that you would expect just by chance on this randomized data, and then compare your cluster size to that. So that's kind of like the second option in here, the permutation randomization analysis, and that requires like, let me see if I had actually run it. Yeah, I did. Okay, so that gives you some, again, using the same high threshold, but a different cluster definition. And in here is another of the difference that Jason mentioned. In addition to getting like cluster size, you can also get cluster mass. So cluster size is basically the number of voxels within a cluster, and cluster mass is basically the sum of the t square values across these voxels. So it's a measure of both the size of the cluster and how strong the effect is within that cluster. So you can base, unlike the random field theory approach, the first option here, the second option allows you to use a measure not only of the size of the cluster, but also of the mass or the strength of the cluster to determine whether a cluster is significant or not. So that's kind of like the second approach.
Is there?
Oh, sorry, go ahead. Yeah.
We could either go into this later, but I mean, just about that. What's the advantage of using one versus the other?
Right. So the advantage of the parametric approach is that it's fast and that is typically most sensitive if the assumptions are held. Basically, if your data is relatively smooth, if you use relatively conservative high thresholds.
Sorry. So I meant the mass versus
the mass versus. Oh, okay. So the mass, there is no theoretical best. Typically, the mass is preferred because it gives you sensitivity to perhaps clusters that are relatively small. So if you find an effect that is relatively small in cluster size, it's very difficult to get it to be significant because it's just a small place in the brain, and there are going to be, like, if you use a relatively normal threshold, the clusters of that same size are going to be just pop up just by chance. So it's very difficult to find something significant if it's really located like in a small area in the brain. So if you want to localize that, then using cluster mass is going to give you just a better metric because it better captures what is particularly strange about this true cluster compared to the random clusters, right? But there is no a priori other than that, like depending on your data, there is no a priori one is version better than the other response to that. Typically, people prefer cluster mass, and typically you will find that it's slightly more sensitive. So if you look at the family-wise error corrected values, it's going to look, they are going to look very similar, for example, but this is slightly lower. So that's kind of like where the higher sensitivity comes about. But the difference is relatively minor. It's not huge. So by default, the recommended procedure, for example, uses cluster mass by default. So if you don't have any good reason to change that, then use that.
Okay. Great, thank you.
No problem. And then the first method is the threshold-free cluster enhancement, which is, I don't know, do you know what this method is about? Have you read it or heard about it before? Nope. Oh,
No.
okay. So this is something that the Nichols group came up with a few years ago already, but actually it also needs randomization permutation analysis, so it takes a while, and it seems that I haven't run it. So while this runs, it just takes a few seconds, well, a few minutes actually. Let me see if I can get some window that shows. Let me see. Oops. Here. Okay, so all of these methods, I don't know if I mentioned this to you, but you can find like a definition of all of these different methods and like a more detailed definition in here in this website. So in the Con website, I made this part of the book actually, so that this is kind of like online, and you can read all of these like method details in a little bit more detail in here. So this is where the threshold-free cluster enhancement like description comes about. You can read about it in more detail here, but very briefly, well, it's again in the same vein as what I was mentioning at the beginning, saying that what people are trying to develop methods or procedures that avoid p-hacking or that minimize the motivation for people to p-hack the results. This method like originated with the same idea. Remember, all of the previous methods use this high threshold that you have to determine kind of like a priori, and then it's the cluster forming threshold. You determine a high threshold that determines some clusters, and then you have these clusters and look at properties of those clusters to determine which one is significant or not. But that gives the user a little bit of, well, they have to choose what is the cluster threshold that I choose, and people either use a priori choices for that, like the recommendation generally is that you use a high threshold that is very conservative or a p-value that is very low. If you expect to find something that is very small and significant, and if you use a relatively liberal high threshold, if you expect to find something that is relatively broad and weak, but very over relatively large areas. That's kind of like the general recommendation. But many people end up just playing with that parameter until they find something. So in order to minimize that, they developed this method that doesn't have any high threshold at all. They say, well, how can we talk about clusters without actually defining a cluster high, without using a cluster high threshold? And they came up with this idea of just defining. So basically, for every voxel you have this computation, which the idea is that if you have like these clusters to think them in one dimension is simpler than in 3 dimensions. But in 1 dimension, you have a line, and then you have the statistics of every voxel in that line that forms some peaks, right? And then when you threshold that line, you have anything that goes above that cluster, above that line in the statistics is your cluster. So instead of having to like draw a line and determine the clusters and the statistics about those clusters, they say, well, for every voxel, we could actually imagine all of the lines that I could draw to cut that cluster into different heights, depending if I use a lower value, it's going to get a larger cluster, and I use a higher threshold, I'm going to get a lower threshold, and I'm going to combine the statistics of all of those clusters that would appear if I were to use all of potential high thresholds. And they came up with this formula basically to define that at every individual voxel level. So you can actually apply to, if these are the actual statistical significance of the voxels and you have a 2-dimensional image instead of a 3-dimensional image, then for every individual voxel, you get it's called TFC, threshold-free cluster enhancement score, that tells you a combination of that voxel, how significant it is, and that neighborhood, the clusters that could be formed if I went ahead and threshold the value, the threshold, the results by some height, how large the resulting clusters would be. So it's a combination of the cluster size and the cluster strength, similar to cluster mass, but it doesn't require you to actually determine a high threshold because it somehow combines all potential high thresholds in the data. And then once you have these maps, these are the threshold-free cluster enhancement scores. You just do statistics on them. You just do randomization to evaluate how would this map would look of TFC scores if I had random data, and then they compare the actual numbers that you get compared to what you would expect by chance to determine what is significant or not. And at the end, you end up with something that looks very similar. Let me see where I had this. Just, well, 20 minutes is going to be too much. But you end up with something that looks very similar to the other two approaches. It just uses a different method for determining what is a significant cluster. The advantage of this method is that you don't have to actually choose. This is kind of like how the cluster map looks, but it hasn't been thresholded yet. So this is the TFC scores what you're seeing here, basically. But it's just a different method to determine what is significant in the results in terms of clusters, but without having to go ahead and define a high threshold to determine what a cluster actually is. So it has that advantage, at least theoretically. And it's very, it also like the second approach, it also needs to run randomization and permutation analysis, so it takes a while, so a few minutes to actually run the analysis. This is an analysis across 200 subjects, that's why it takes about 20 minutes, but it's still manageable time. It's not days or anything like that. Okay, so that is the third method that is also available in here. And for every method, sorry, I'm going to switch to before doing this. For this. Okay, so for any method, any of these three default methods, you can actually go ahead and change the details in here. If you don't like the default settings for that method, you can select the fourth option and then go ahead and change that and use a different high threshold, for example, here, or use a different method for determining which clusters are significant. Just selecting here a different option.
Alfonso, can I
to how it was before? Sorry, go ahead.
Can I just get a clarification? When you switch to this window here, or this pull down for the show details, if I were to change parametric stats to non-parametric stats, am I effectively just changing it to the randomization permutation method?
Exactly.
Okay.
Yes, exactly. I mean, this gives you like all of the flexibility. All of the individual, these three methods are actually just some particular combination of these parameters. But those particular combinations are not always obvious how to get them. So that's why we have these three default methods. It's typically simpler to go here, then go to the details to see the details of this particular method, and then you will see here non-parametric stats for that, and using cluster mass instead of anything else, right?
And the random field theory option is not available for surface-based analysis at the moment, right?
Exactly. At least at the moment, that's the problem with. That's because the theory, even though it has been developed for general fields, and that includes two-dimensional fields, like in the surface, most of the implementations only have implemented the three-dimensional version of those. So the mathematical theory is there to actually determine cluster significance of the size of a cluster on a two-dimensional surface, which is what we would need for surface-based analysis. But well, at least I haven't gotten around to implementing it, and I don't know, I will have to look at the details. I don't know if anybody else has implemented the two-dimensional version of random field theory statistics. I know mathematically it's possible to do that, it's part of the theory, but I don't know if any implementation has tried. So yeah, in practice, right now, if you have, sorry, go ahead.
Is the threshold-free cluster enhancement, is that an option for surface-based analysis?
Yeah, definitely. You have the last two. So basically, you have the same. Number one is not available, but number 2 and 3 are available.
And would you recommend that method at the moment? Like basically, like the last.
Yeah, I like the threshold-free cluster enhancement method. It's very cool. And I think the theoretical advantage is of not having to determine a high threshold is a good enough one to recommend it in general. I don't know. It's perfectly. I think in general it should give you similar or better results than the non-parametric approach, the standard non-parametric approach. But I haven't run it yet on sufficient data to actually figure out whether that is actually general or just happen to be in the few cases that I've run it. So yeah, it's a perfectly recommended method. It's very popular. It's used a lot, and there are a bunch of different implementations out there to use it. And well, I got around to implement it in here. So now you have the option to just use it in using the same GUI and actually compare the results of using this method versus anything else. So
okay.
Nice. Let me see what else. Another thing that Jason mentioned is that you can actually look at, if you look at an individual cluster, you can actually see here the list of where that cluster is. And it tries to tell you that in terms of a few reference atlas. This was already before in the previous version. But so basically, if you want to know where this cluster is, it tells you that this is, I don't know, close to visual areas, right? So it's going to tell you that it's occipital. And these many voxels are covering 40% roughly of the occipital pole left, and the same thing in the right. It's just like a general description. If you have to go ahead in your paper and describe this cluster in terms of where it is, in terms of anatomical regions, you can use that. But if you don't want to use this kind of default regions, you can right-click on in this and change the reference atlas. And that will basically compare this cluster to whatever atlas you want to use as reference, right? So if, let me see what I have here. I think I have in here some, I don't know, this is the ROIs, details, other ROIs. I don't know, this is, I was looking here for one that is called, the Geo. I don't know how to pronounce it. Do you know how to pronounce this name?
I think it's Yo.
Geo. Okay, so Geo
I
is one also relatively popular atlas. Is only actually, what was I playing with this? Yeah, I was probably. Okay. Okay, this is just an atlas in terms of 7 actual regions that are relatively like the full mode network and salience networks and things like that. So it's a very broad atlas. It has 7 regions across the entire brain. It has another one that has, I think, 14 or 15, I don't recall, version, but just as an example, basically. So you can just change that reference atlas to use whatever regions you want, and it will tell you each individual cluster where it lies with respect of that, the regions defined in that atlas. That's the functionality that is in there. Let me see, what else is new?
Alfonso, what is the default atlas we use right now?
It's the Harvard-Oxford Atlas. It's described in here. So when I look at the details of that, it's called...
Would you...
So this is this is part of the control box ROI's atlas.info describes where this atlas comes about. This is FSL Harvard Oxford that is mixed with AAL atlas because the Harvard Oxford doesn't have cerebellar parcellation. So AAL has a better parcellation of the cerebellum, so that it uses a combination of those two. You were going to ask a question, Jason, sorry.
Yeah, would you object to, or to us like moving our surface-based and volume-based atlases for the speech lab parcellation to that same directory, or would you be better to just have people point to that where it is in the SLROI's directory?
Right. So this atlas is the one that is going to be used by Con by default for ROI. So it's not great to override that.
I see. So that's just the one. Okay.
Yeah.
So
I mean,
is there a place?
I can make the option in FL just to specify the atlas, and I can make it as part of our FL functions to use a different reference atlas.
Because there is
by default.
There is in FL there is a directory that's ROIs, right? That has the atlases, or is that not the case?
You mean in FSL or what?
In FL, in the FL pipeline,
in FL.
somewhere in that directory of the FL software, I thought we did have a repository of atlases that we might use.
Right. I know of the speech lab ROIs directory that we have in SEC, but FL is not. But basically, it's not part of FL itself. I mean, we have the. What was it? Let me see if I have it here. This is. Where am I? No, this is a different. Sorry. So actually, I have this question for you, Jason, as well. This has come up a couple of times. Let me just get to this first. There was a ROIs here, right? Sorry, it's in actually project MB, just below. Yeah. So this directory is the one that you mean? Sorry.
Yeah. So there's a directory in there that's SLFSAVG,
right.
and then that'll have that has the SL average as nifty files and the volumes, and also the surface versions of it.
Right. So I had this question for you. For this directory, actually, which one is the version? Our regions are defined from free surfer parcellation, right? So they are defined actually in the surface, but sometimes we want these regions to be like on the volume so that we can actually categorize what is the closest area in MNI space, right? If I have a voxel in MNI space.
Right.
So which one is the version that you would recommend for that, and how is that created?
Well, so we have that version in, so I believe that the SLFS average A plus aseg.mgz and what follows would, so I think there's a nifty version of it too. Right. That's the volume, like the MNI 305 volume.
And is it
But
defined on which space? So it's basically projecting like FS average PL surface, or is it using the? I seem to recall
right,
that
so
you have taken one of these like templates in M&A templates and run it through FreeSurfer to get a
right.
better.
So what I was going to say is, like, I think a better option is I'd have to hunt around a little bit to find it. But I am on the SEC, so I can do that. So we have an option where I did the M&I, was a M&I 151 or 152 template, the volume template. So we labeled that, we labeled the surface on that, and then ran that through FreeSurfer to generate a full volume. And I think that's a better option if you want to use a volume template than.
And where is that located then?
Let me take a look.
Also, in the meantime, let's see. I think it was. See if I have it in here
So, and
should I have it in here somewhere?
almost there.
Let me just look for it then.
Okay, so if you I'll just confirm this before I start giving you.
Okay. So just this was to show you like something similar that these guys did for getting this other cortical atlas, which was also defined on the surface to get it into like an M&A space version. And they did something similar. I believe they took like one template, I don't know which one, but they took one template and run it through FreeSurfer to get like this nice delineation of the cortical ribbon within it, and then they associated the labels with that, which I imagine is also what we did, and then they kind of like glue it. I don't know the procedure. I'll have to read the details, but just to make it a little bit thicker, because otherwise, I mean, you end up just looking at when you apply this to an arbitrary volume that hasn't been run through FreeSurfer, that doesn't necessarily match all that well with the cortical ribbon. So they just grow that in order to make that into an M&A version of the file. So. Okay, that was just to entertain you while you were looking for it. So what it is.
So what may be the case is that I have not generated the volume atlas from this. So let me get a label here. So we have, okay. Okay. So if you, in that same directory, so SLROIs, there's a directory called template_volumes. And then there's a directory called FS_MNI 152.
So it was MNI, it was FS.
It's FS
yeah.
MNI.
Got it.
And in there, in the label directory, I have the annotation files.
Cool.
For the automatic parcellation.
Oh, okay. So
but what I don't, right,
right.
So look, I thought we had moved on. We'd done a little bit more than this, but maybe not. So what we need to do is create the surface-based version of those. I'm sorry, in the format.
Right, the Nifty, we can convert this to Nifty, basically.
And then I also need to run the APARC to ASEG on this. So I need to take these and then map them into the volume, because that's not available yet.
Cool.
But that's a piece of cake.
Cool. And perhaps we can actually then follow something. I'll check what they did in that paper,
Okay.
but probably we should also kind of like grow it a little bit to make it like thicker, those regions, so that it generalizes to other kind of like general M&A space data that I might not have necessarily gone through FreeSurfer actually. So.
Okay.
So it would be good to actually generate that as a reference atlas for ourselves, right? And then I can make that the default atlas to be used for as reference when displaying any like volume or surface level results. write down where this is. Then it's in, let's say otherwise template. And the template, what template is it? Is it like an average of many brains, or does it actually look like a relatively reasonable brain?
It's the MNI 152, which is it is an average, but it's, or I should say, it's the way that it works. It includes, I think it's 152 brains, but it's not an average like 305 is. It actually looks like a very high resolution individual scan.
Okay. So first of all, it doesn't have
So
any
they
trouble
do like
like
this,
parcellating
like,
it and right.
it parcellates very well. It's actually like it's a great template if you're going to use. So in the most recent version of the slice series that I've used for figures and papers or chapters to display where our regions are, where activation is, I use that template because it's such a nice looking one.
So I should be able to find it here basically. So this T1 file in this directory should be that template, right? That you're using.
Yeah, and that if you want the actual original of the template, it's
Right.
also,
I will have it here as well. Yeah. Right.
Yeah, and there's the directory. If you go up a directory, or if you go up to the template volumes directory, you'll see that there's an MNI
The one, the
ICBM 152,
ICBM.
and then that
Okay,
has
cool. Excellent.
that tells you that title, the name of that file, the MNI IC or directory, MNI 152 non-land. That is, you can find that online.
Right, and this is the like a 1 millimeter voxel resolution. I think
this one is, it can be a higher resolution. I think they have it down to a 0.5 millimeter. And there's actually a new one that came out recently that kind of interesting to look into.
Is it the same as this one? I'm not entirely sure which one is this, but it looks like that because this is like
it could be.
Reference.
I know that this
like
template is
ridiculously high resolution stuff.
It looks a lot like that, and I know that both FSL and SPM include this.
Okay, I think I took this from FSL as well, so I'll add that. Okay, I'll double check that. Okay, that would be excellent. So yes, this would be fantastic to have that version of our speech lab ROI is projected into this kind of like MNI template brain, then grew and then just exported as a mask that we can use as for reference or even for ROI definitions for MNI processed functional data, right? If we want to skip the free surfer for whatever reason.
Yeah.
Cool.
A very basic question back on the GUI is, you see where it talks about there are the number of voxels covering 8% of this ROI. Is it possible to also add what percentage of the cluster is?
Right. I mean, so basically this 1800 compared to this 2200.
Exactly. Yeah.
Yeah. I can add it in here, like that many voxels, like whatever percentage covering whatever percentage of the cluster itself.
And one thing I wanted to test, Alfonso, was the last time I tried this on the SCC. When I right-clicked on that, I got the export option, but not the choose Atlas option. So
this I added a couple of days ago. So basically, that might be like actually, yeah. Well, why is not showing that? Huh.
I think you gotta go to the one below.
Perhaps that's a good example. Okay, I know because it's the one lower here. You mean this one?
Yeah, so I wasn't getting that. So can you? I'll test that again.
Sure. I added this like a couple of days ago, so it might not have been there yet, basically.
Okay.
Another thing that changed in the latest version compared to the previous one is that now when you display the effects within each cluster, it's a little bit more descriptive because it saves all of the information about how each, what each define is, what each like design matrix is for your second level analysis. So it can tell you a little bit more about this. So this, for example, is I don't know why it's so slow. Oh no, this is not that. Oh, I was looking at, well, this is not all that informative. Let me see if I can show you something that has a design that is a little bit better for the purpose of what I was going to say. So, yeah. So I have it. Yep. So basically before, when you were displaying the effects within each cluster, the effects would be the contrast values, which depends on your experimental design, might or might not be something all that easy to interpret. And now instead of showing you the actual contrast values within each cluster, it shows you the raw effects that were originally used to define the contrast. So for example, in this example, we were looking at like males versus females. So instead of telling you the difference between males and females, it actually shows you the actual, I don't know, these are connectivity values, but anyway, otherwise it would be activation within males and females. So you can interpret those results a little bit better than just looking at the difference. So before it would just show you one bar in here telling you that, I don't know, the difference between males and females was close to 0.1, but you wouldn't know if that meant that it was, well, it was perhaps connectivity high in both, and it was just 0.1 higher in one group versus the other one, or it was, I don't know, perhaps it was negative in one group. And so looking at the results in each individual effect that that was used to construct the contrast is typically a little bit more informative. So this display should be, in the new version, should be a little bit more informative than what they used to be before.
Hey, Alfonso.
Yep.
So regarding that specific plot,
Mm-hmm.
so for the rhythm study, I basically just looked at the rex.mat file and kind of sifted through to the results to find the like effects and the confidence intervals. Is there, it might be helpful to have like just something that you can easily export, like just the means and confidence intervals without having to go through and find that specific rex file,
Right.
and to be able
Right,
to
that's a good point. I could perhaps add an option here to export these stats basically on these actual values. That's a good point. Yeah, thank you very much.
And then also regarding this screen, the when it lists the p-values of these ROIs, is that just the what do these p-values represent? Because they're not the same.
They are post-hoc analysis. They are the whatever contrast you're using here. And here we are, for example, we are looking at the difference between the two groups, right? So you get a statistics for every individual voxel, and then you get whatever significant clusters. So when you display here, you get these voxels, and you figure out what is these are connectivity values, all right? So you are looking at the average connectivity within these same voxels for males and females, and then it applies the same test to that average connectivity value across all voxels within your cluster. And that is what it displays here in terms of the statistics. These are all post-hoc analysis because they are the cluster selection is based on the same threshold that we are showing here, based on the same statistics that we are showing here. So you shouldn't trust these values. They don't pay too much attention to those because those are going to be inflated. They are biased to show you like ridiculously low, very highly significant results just because of the nature of the clustering procedure. Sometimes when you use this display, you don't have to necessarily use these same clusters to show the results. You can change this. You can say, well, instead of show me these results, show me still the difference between males and females, but don't do it based on these same clusters because I don't know, I want to look at something else. So you can actually select the clusters using a different procedure. And as long as that is orthogonal to the question that you are asking, so those come from an atlas, for example, or they come from a different contrast in your same data that is not related to the difference between males and females, then those statistics can be trusted because those are going to be just summary statistics based on this a priori definition of clusters of what is the difference between males and females and connectivity values within those clusters. So in those cases, you can trust those values. But if you use kind of like the default setting thing here and just use this button to display the effects within these clusters, since these clusters have been defined using the same statistics, you cannot trust those post-hoc statistics.
Okay, great. That's what I figured.
Cool. Okay. Well, I think that's it. Do you have any other things that
I
you'd
have a
like
question
to
for
talk
you,
about?
Alfonso.
Sure.
So I've been playing around with this with Matt's data, and when for his volume-based analysis, and what I found is that, well, if we correct this, seems like if we correct this in a responsible way, we don't see anything. But then I just wanted to start playing around to see where the activation was. And what I found is that if I set some ridiculous cluster size threshold, like 0.5, and I switch between non-parametric and parametric stats, the clusters that show up are very different. So I'm wondering, is there, why is that the case? What I would have thought is that the clusters would be, because I'm thresholding at the same voxel level, that's the same. So it's just in the cluster thresholds that same ridiculous value.
Right.
Why would the clusters themselves be so different?
Let me see if I can. It should be exactly the same. So if it's only that the high
okay.
threshold between these two versions is slightly different. So let me see if I can show you the high threshold in the version 1. So in the first recommended values and the second, these guys are using a high threshold of 0.001, and these guys are using a high threshold of 0.01. And then these guys don't use any high threshold at all because that's the wrong method. So if you just switch in between these two, the clusters are going to be different because the high thresholds are actually different. But if let me see if I can change that so that it shows something, even though it doesn't. I don't want to wait a few minutes, so I'm just going to change that to display the actual clusters. Okay, so it's just showing all of the clusters at this high threshold. Let me actually show it at this threshold, which is the one that the other method is going to show. Right. So, okay, so these clusters should be exactly the same, at least whichever shows as significant. Let me see, as the ones in the first method. So this is this is using the non-parametric statistics thing. But if I switch this to parametric, I should be getting exactly the same. Yeah. So at least these first two, right? They are exactly the same as they were before because you're using the high threshold, and just what is changing is all of the cluster statistics. They use different methods to determine what is the statistics associated with this cluster, but the actual cluster and the size of that cluster should be exactly the same.
Okay. Okay. I'll go back and just see what play around and just see that. I mean, that's how it should work.
Right.
So I'll go back and see what it was that maybe something I changed something.
Well, there is an exception, but I don't think you are running into that exception, but it might be. I mean, there is an exception to this where the method used in here uses a different statistic for the. So basically, when you run an F-test that has multiple effects, so let's say that you're looking at the difference between 3 groups, and you are running an F-test to determine what is significantly different between the 3 groups in terms of the activation or something like that. There is an F-test that involves difference between the first and the second group and the second and the third. And the parametric and non-parametric approaches use slightly different voxel level statistic approaches. So when you use, at least for this kind of F-test things, when you use permutation randomization analysis, the statistics at each voxel level are computed using what's called multivariate analysis. So basically they actually try to estimate freely across each individual voxel the covariance between the things. So for example, if you're, let's say that you are measuring like let me see, like 3 conditions. You have speech fast and slow, and then you have something else. These 3 speech conditions, you have activation across the 3 conditions, and you want to see whether there is any difference in activation at some region across these 3 conditions. You can run an F-test to actually evaluate that. And the non-parametric approach that uses multivariate statistics is going to look at for any individual voxel, is going to look at the activation in the fast condition versus the slow versus the third one. And it's going to try to freely estimate the covariance between the 3. So you're going to have like a 3x3 matrix that characterizes the level of covariance between the across subjects. This is the across subject covariance between the activation levels across each of the individual conditions. And from that covariance and the actual size of the difference, it spits out a statistic value, basically an F value. On the other hand, the parametric approaches, the random field theory approach, don't use this multivariate analysis for estimating the covariance between multiple conditions. They use this restricted maximum likelihood approach. So instead of assuming that the covariance might be different for every individual voxel, they assume that the covariance has exactly the same shape across all of the voxels in the brain, and that there are only differences in the scaling of this covariance. So they assume that the difference between the covariance, the 3x3 covariance of the activation in this particular voxel and the 3x3 covariance of this other voxel, they are identical, they are just different by a scaling parameter. And they use a different method to estimate that. And because of that, they spit out a slightly different F statistic value for that individual voxel, because one uses multivariate analysis and the other one uses this restricted maximum likelihood approach. So in those cases, then yes, you're right that if you use whatever high threshold that you use in one method, it's not going to give you exactly the same clusters as using as a high threshold in the other approach, because the F statistics underlying those p-values that you're using for high threshold are actually slightly different between the two of them. But that only happens when you have multiple conditions that are estimated jointly in an F test. If you are looking at something like that, like this, for example, in like a t-test that gives you a t-statistic, those are exactly the same. The restricted maximum likelihood approach and the multivariate approach gives you exactly the same statistics in two cases, and that's why you see that when you specify a high threshold, you see the same clusters in the two approaches. Makes sense?
Sure. All right.
Okay. Any other
Okay.
questions?
So the other questions I have are very specific to what I wanted to do is just walk through some of the config files that Matt's using for his three main. He's got two for his surface and volume-based analysis and the two different contrasts. So that, I think, Alfonso, we could. We've been on for a while, so we could walk through that now if you're up for it, or if you wanted to take a break and do it later, we can do that too.
I can continue and we can look at that, but everybody else, if you want to just break, go about your business, that's perfectly fine.
I will jump off here. So Jason, I'm just going to make you host, just so in case, I don't know what happens when I leave.
Okay.
So you're now host. So
great.
there you go.
We're all very sad when you leave. That's what happens, Elaine.
Thanks, Hillary. Okay, see you guys tomorrow.
Okay, bye, everyone.
Bye.